Hello everybody. Let me welcome you to our today lecture dedicated to vectors. In this lecture, we will talk about scalar and vector quantities. Then we will study a unit vector, magnitude of a vector, and then we will study the operations above the vectors, which are addition and multiplication. And multiplication can be implemented in the form of dot product and cross product. When we will study the cross product, we will study how to calculate a determinant. And then we will look at some interesting facts about dot and cross product, which are the commutative property and Lagrange's formula. In our nature, we can operate with scalar and vector quantities. A scalar quantity can be described by using a single number, the magnitude or size. For example, we can have a distance from point P to point Q, and this distance will be a scalar. Or we can have a ship that sailing at the speed 12 kilometers per hour, and this speed will be also a scalar. A vector quantity has both magnitude and direction. For example, from point P to Q, we can go 100 meters north, and this displacement will be a vector. Or our ship can be sailing at 12 kilometers per hour on a bearing of 60 degrees. And this is called the velocity of the ship, and this will be also a vector. Magnitude of a vector. The magnitude of a vector is the distance between its start point and end point. We can have a notation for vector A, and we can have a notation for vector AB. Sometimes we call modulus instead of magnitude, and the magnitude is a scalar and it's always positive. Let's talk about unit vectors. Unit vector is a vector that has a magnitude of 1 unit. Some unit vectors have been defined in standard directions. Our x direction specified by unit vector I, y direction specified by j, and z direction specified by k. We can also specify n as a vector normal to a surface. Finally, for example, we can have this vector 3i minus 5j plus 8k, and the hats show us that they are unit vectors, not the variables. And also this 3i and minus 5j and 8k are the coordinates of our vector, or x component and y component and z component of our vector. Let's take a vector from our previous slide, 3i minus 5j plus 8k, and we can sketch it in our 3D space, so we can see our coordinate system x, y, and z, and we can see the unit vectors I, j, and k that correspond to the directions of x-axis, y-axis, and z-axis. And our blue vector has the coordinates 3, minus 5, and 8. Also, we can multiply our vector by any number. For example, if we multiply it by 1 over 2, we will obtain our new vector, so it will be twice shorter, and the coordinates will be 1.5 in the x-axis, then minus 2.5 in y-axis, and 4 in z-axis. We can see this red vector. To find magnitude of a vector, we can use this formula. A equals square root of ax squared plus ay squared plus az squared, where ax is the magnitude of x component, ay is the magnitude of y component, and az is magnitude of z component. For example, if we take our vector from previous slide, 3i minus 5j plus 8k, we can calculate its magnitude as square root of 3 squared plus minus 5 squared plus 8 squared, which is equal to 9.899. Now let's talk about the operations about the vectors. And our first operation is vector addition. Let's take these 3 points. We can travel from the point P to point Q, and then from Q to R. And we can see our resultant travel PR. And in vector form, we can express this through the vectors PQ, QR, and PR. And our resultant vector PR equals the sum of PQ and QR. If our vectors expressed using the unit vectors I, j, and k as the following: A equals AXI plus AYJ plus AZK, and B equals BXI plus BYJ plus BZK, we can calculate the sum A plus B as the following. We take the corresponding coefficients at the unit vectors I, j, and k. So ax plus bx times I plus ay plus by times j, and plus az plus bz times k. Now let's talk about vector multiplication. Our vector multiplication can be implemented in the following forms. First, dot product. This is also known as scalar product. The second is cross product, and this is also known as vector product. We have to distinguish these two forms very clearly. If we implement dot product, our two vectors are multiplied together in such a manner as to give a scalar answer, magnitude only. So the result of our dot product will be a scalar. If we implement cross product, our two vectors are multiplied together in such a manner as to give a vector answer, magnitude and direction. So the result of our cross product will be a vector. Now let's implement our dot product. If we have the vectors a and b expressed as the following: a equals axi plus ayj plus azk, and b equals bxi plus byj plus bzk, where ax and bx are the x components, ay and by are the y components, and az and bz are the z components. We can calculate our dot product of the vectors a and b as the following. We take corresponding coefficients at I, which are ax and bx, and multiply them. Then we add the multiplication of corresponding coefficients at j, which are ay and by, and then plus corresponding coefficients at k, az times bz. And of course, when we multiply the coefficients of I, j, and k, we obtain a number, so our answer will be a scalar. If our vectors are given graphically, as in this diagram, so we know their location, we know their magnitudes, and we know the angle between them, we can calculate dot product using this formula. So our dot product equals multiplication of their magnitudes and cosine theta, where theta is the angle between the vectors A and B. We can use our previous formula for finding the angle between the vectors A and B. So our theta equals r cosine of the fraction, where in the numerator we have the dot product of AB, and in the denominator we have the multiplication of their magnitudes. So if we take the vectors A and B, such as 2i plus 5j and 4i minus 3j, we can calculate our cosine theta. And if we don't have the z components in our vector expressions, it means that our vectors A and B lie in the xy plane. So let's calculate our cosine theta, and this will be equal to this expression according to our formula. So we have the fraction where in the numerator we have the dot product, and we multiply the corresponding coefficients at I and j, and then we sum them up, and in our denominator we have the multiplication of the magnitudes, which are root of 4 plus 25 and root of 16 plus 9, and this equals to minus 7 over 5 times 29. If we take our cosine of this expression, we will obtain approximately 105 degrees.